This recording will start to look at Chapter 1, which really looks at a broad brush version of what climate is and the hot topics today, and then looking at basic atmospheric variables. So the climate system is really a complex network of interconnected systems. On the lower left here we see the atmospheric circulation drawn out, and on the lower right we see the oceanic circulation drawn out. Both of these systems we'll study in detail in Chapters 4 and 5. Chapter 1 key points. Climate change has recently moved into focus with the media and the general population. People are talking about climate change more than ever. The Intergovernmental Panel on Climate Change, the IPCC, plus Al Gore, won the Nobel Prize in 2007 for their efforts. 97% or more of climate scientists agree that humans are causing global warming at this time. Here are some numbers from the scientific consensus on climate change. In 2009, a study showed that out of 79 scientists, 97% of them said that humans are a factor in global warming. In 2010, out of 908 scientists, 97.5% agreed that humans are a factor in global warming. In the most recent survey in 2013, out of 10,000 climate scientists, 98.4% agreed that humans are a big component. Studying climatology requires a firm understanding of the physical controls on climate, and this will be a key component to this course. Looking at things like astronomical factors, Earth's shape, orbit, the tilt, the wobble of Earth, plus sun's radiation and its cycles, and how these all play together to affect phases of climate. Also terrestrial factors, including the gases and clouds, the surface characteristics, oceans, the continental shapes and positions, the phases of water, other means of energy transport, etc. This graph is showing a surplus of radiative energy at the tropics and subtropical areas and deficits at the poles over time. This is an annual average graph. As a result of having a surplus in the tropics and a deficit in the poles, there must be some means of energy transport to move the surplus towards the deficit. This is accomplished by the atmosphere and the oceans in a variety of ways. Notable climate topics pointed out in your book in Chapter 1 include economic impacts of climate, both future and present, climate and human activities, for example, how Inuit hunting techniques have evolved with climate change, satellites. Satellite imagery began in 1979, so we now have a long enough record to establish climate studies. Teleconnections, these are remote climate impacts from large-scale phenomena, for example, how El Nino in the equatorial Pacific impacts U.S. weather, and great improvements in computer and data. This graph is showing the rapid rise of computers' power over time by looking at the top 500 supercomputers around the Earth. On the y-axis is shown as gigaflops, billions of operations per second, increasing logarithmically. Now we see for the top 500 supercomputers increasing logarithmically over time. The United States have 4 of the top 10 supercomputers, and they're often used for climate runs. Climate studies are one things that force computational demand in the industry. The National Center for Atmospheric Research has responded to this demand by putting a supercomputing center in Cheyenne, Wyoming. Here are some examples of what this computer can do as far as data visualizations. First, looking at water vapor in the global atmosphere. Now looking at cloud microphysics. Moving on to sea spray and high winds. This is something that's very important to resolve, looking at hurricane activity. And finally, looking at ground velocities in the California earthquake here. The atmosphere's most pivotal roles. First of all, we've all heard of the greenhouse effect, but it turns out without greenhouse gases in our atmosphere, we'd be 60 degrees Fahrenheit colder than we are presently, which means that those of us living at the surface would definitely freeze. Protection from the most harmful ultraviolet radiation, which is called UVC radiation. Ozone protects us from that, so it's a key feature of the atmosphere. Along with the ocean, the atmosphere transports heat and moisture from the equator to the poles, but also from the surface to the upper atmosphere. So in essence, it redistributes energy around the globe. Climate versus weather. From the National Oceanic and Atmospheric Administration, here's their statement. Weather reflects short-term conditions of the atmosphere, while climate's the average daily weather for an extended period of time at a certain location. It is important to understand, though, however, when you characterize climate, also variations and extremes. The extremes can have long-lasting impacts on the land surface and otherwise. For example, if you just used average Boulder statistics, mostly dry and sunny, you wouldn't have any notion as to why Boulder has very large floodplains.
Okay, so if we scientists are so good at making these dire long-term predictions about the climate, how come we're so lousy about predicting the weather? Besides, this year, we had a colder winter in my town. For all the scientists know, we could be in for global cooling. Here's the difference between weather and climate. Weather is what the atmosphere does in the short term, hour to hour, day to day. Weather is chaotic, which means that even a microscopic disturbance can lead to large-scale changes. That's why those 10-day weather forecasts are useless. A butterfly flaps its wings in Bali, and 6 weeks later, your outdoor wedding in Maine is ruined. Climate is the long-term average of the weather over a number of years. It's shaped by global forces that alter the energy balance in the atmosphere, such as changes in the sun, tilt of the Earth's axis, the amount of sunlight the Earth reflects back to space, and the concentration of greenhouse gases in the air. A change in any of them affects the climate in ways that are broadly predictable. My friend's meandering represents the short-term fluctuations. That's weather. It's almost impossible to predict what will attract his interest next. But not hard to know what the range of his meandering will be, because I'm holding him on a leash. We can't observe climate directly. All we see is the weather. The average weather over the course of years reveals a pattern. I represent that long-term trend, which is climate. Keep your eye on the man, not the dog.
To start to look at how we understand climate, we have to understand our observations, both in situ, meaning on site, and also remotely. What variables are commonly observed in the atmosphere and the oceans? What instruments are used to record them? Here are some examples of commonly observed atmospheric variables. Temperature, pressure, current weather, is it snowing or raining? Solar intensity, how strong is the sun at any given moment in time? Dew point temperature, which is a measure of the moisture amount. Cloud types, their heights, the amounts of clouds throughout the sky, the precipitation rates and totals, and the wind speeds and directions. Upper air observations are taken from radiosondes, satellites, commercial aircraft, Doppler radars, wind profilers, and more. Radiosondes are simply weather balloons with instrument packages that measure common variables like temperature, pressure, and moisture amounts. In the oceans, observations are taken from satellites, boats, and buoys. The oceans are very important for climate since they cover 70% of the Earth. Surface observations come from many unmanned automated stations and also manned weather stations such as at airports, plus satellite observations as well. The raw data from all these observations is processed and disseminated by organizations throughout the country and throughout the world. Computers can use statistics to provide reasonable global data, even with sparse raw data in some locations, like for example in the remote mid-Pacific. Oceanic measurements are shown here, with just one map over time showing the location of both moored buoys and also drifting buoys. There's a big array of moored buoys along the equatorial Pacific, and this is because they're looking at the phenomenon called El Nino, which we'll study in Chapter 5. Along the coast of the United States on the west and the east coast, there's a number of moored and drifting buoys that are measuring sea surface temperature and salinity. Some drifting buoys are advanced and can actually sink throughout part of the oceanic column, record temperatures and salinity measurements throughout the column, and then float back to the surface to disseminate their information via satellite. Those were some examples of modern observations, but how do we observe what happened in the far past? Well, people haven't always been around to directly observe the state of the climate, so we have to infer these past climates via climate proxies. Some examples of climate proxy data include ice core records, tree rings, plant distributions, fossil records, ocean and lake sediments, spores and pollens in the fossil records, coral reef cores, and much, much more. Here we're going to go over some atmospheric basics. The pressure in the atmosphere that you experience is literally due to the weight of the atmosphere above you pushing down on you. Thus, when you go up in elevation, say to the top of a mountain, there's simply less atmosphere above you now, and less weight is felt as a result, and therefore pressure always decreases with height. Temperature typically decreases with height in the lower atmosphere, but this varies substantially with time, and it certainly varies as you go even higher in the atmosphere. This graph is showing the change in air density and air pressure as altitude increases. It's showing an exponential decrease in both air density and air pressure as you go higher in the atmosphere. This is a result because the atmosphere is an unconfined gaseous fluid resting on the surface. Due to that air's mass and compressibility, this pressure and density must decrease with height. This graph is showing the atmosphere split into temperature gradients, changes in temperature with altitude. Here we're showing what's called the troposphere, where in general temperature decreases with height. The stratosphere, higher up in altitude, from about 15 to 45 kilometers, temperature increases with height. And then the mesosphere, very high up in the atmosphere, going from about 50 to 80 kilometers up, where temperature again decreases with height. Above that is known as what's called the thermosphere, where temperature again increases with height, the topmost layer of the atmosphere. This area separating the troposphere and the stratosphere is called the tropopause, and it's thought of as the atmospheric lid. By that, it means that it resists vertical motion. So any kind of storm trying to penetrate through the tropopause meets resistance, and typically storms cannot push through the tropopause because of its stability. Weather, therefore, is contained in the troposphere where we live. Here's just a visual example of what the atmospheric lid does, the tropopause. Here's a big thunderstorm off Africa over the ocean. It's pushing up, it's rising, warm air is rising, warm moist air is forcing condensation. It's hitting the tropopause, and you see a little overshooting top here, probably because the updraft of the storm is very strong. However, most of the storm is spreading out horizontally because it has faced this atmospheric lid. All you need to do to look at why the atmosphere is structured this way, temperature-wise, is look for the sources of heat. At the surface, we're constantly absorbing solar radiation, so therefore there's a source of heat where we're warmest near the ground. As you get away from that source of heat, it simply cools. There's another source of heat by ozone absorbing ultraviolet radiation in the stratosphere, and that's why the temperature increases with height there. In the mesosphere, temperature decreases with height because, again, you're getting away from any source of heat, so we cool. There is one more source of heat in the thermosphere where actually oxygen and carbon dioxide are absorbing really intense UV radiation. Looking at the composition of the dry atmosphere below 80 kilometers, we see that 78% is nitrogen, molecular nitrogen, N2, and about 21% is oxygen, molecular oxygen, O2. About 1% is the inert gas argon, and then the trace gas carbon dioxide is in here. Of course, this book's a little dated, so we have to update our carbon dioxide, which is now greater than 400 parts per million in the atmosphere. These gases are considered well mixed in the atmosphere. However, this is only considering a dry atmosphere. If you put in the most variable gas, H2O, water vapor, that varies from close to 0% in very dry places like interior Antarctica to almost 4% in very wet places like the rainforests on Earth. Water vapor plays a very important role in climate through many processes, including hydrologic processes, cloud formation, latent heat budgets, and also radiation effects. Aerosols are airborne dust and soot particles. They can act as condensation nuclei for clouds. What that means is if they're around, clouds can form more readily. If they're not around, it's harder to form clouds. Therefore, these aerosols can alter cloud budgets and indirectly alter the radiation budget as a result. These aerosols can also directly absorb solar radiation, or they can reflect and scatter it, depending on the colors or what type the aerosols are. They therefore can directly alter the radiation budget as well. Aerosols and their effects on clouds are the largest sources of uncertainty in climate prediction today. Here's an example from an IPCC report looking at the radiative forcing of climate between 1980 and 2011 by a variety of species. Here the lower axis is looking at radiative forcing in watts per meter square, how much energy per second is being forced over each meter squared at the surface. Carbon dioxide has the most forcing over that time period. This big red bar here goes into the total to affect the total the most, with some error on that, but not a substantial error. I also want to point out that most of the uncertainty on this total anthropogenic component comes from the aerosol studies, where we think they cool a little bit directly, meaning that most of the aerosols we put up there act to reflect a certain amount of solar radiation, and also the aerosols we put up there have created more clouds as a result, which again reflects more solar radiation, giving us a negative component to the radiative forcing. But we're not so sure with our studies. These are hard things to model, and so this uncertainty really compounds our understanding of how this happens. One thing's for sure from the study is that CO2 is definitely forcing positively the radiation at the surface. However, a lot of uncertainty exists from the aerosols. As an example of how much aerosols can actually affect cloud budgets, here we're looking at what are called ship tracks. Ships emit a number of aerosols from their smokestacks, and these can act as condensation nuclei. As these ships went underneath this almost saturated layer, they kind of tipped the scales so that clouds could actually form because we emitted more aerosols to this air. So you might look at all these ship tracks and how many clouds formed on them, and really this can show how much they can affect the radiation budget. Key points for Chapter 1. Climate describes the average regional weather patterns and its variability over a long period of time. Energy coming in from the sun is redistributed over Earth's surface by ocean currents and winds. A region's climate is driven both by its local radiation budget and this movement of heat and moisture by the winds and the ocean currents. Climate data comes from a variety of sources, and it's vastly improving over time along with our computer power. The atmosphere has four main layers when it's differentiated by temperature gradient: the troposphere, stratosphere, mesosphere, and thermosphere. The troposphere has about 78% molecular nitrogen, 21% oxygen, and many trace gases, including carbon dioxide. Water vapor is highly variable due to oceanic sources and also sinks in the clouds. Aerosols, airborne dust, both directly and indirectly affect the radiation budget. They introduce the most variability in climate predictions today.